Welcome everyone, I'm Elon Wu. Today I'm going to talk about gradient normalization for generative adversarial networks. In previous works, the normalization for GANs mainly focused on gradient regularization or applying Lipschitz constraint on discriminator. These kinds of methods can be characterized by three properties. The first one is the model-wise or module-wise property. For example, gradient penalty considers discriminator as a general function. So we think gradient penalty is a kind of model-wise constraint. In contrast, spectral normalization is applied on each internal layer of discriminator. So the spectral normalization is a kind of module-wise constraint. And in Theorem 5, we prove that the module-wise constraint may overlimit the Lipschitz constant of discriminator. So we argue that model-wise constraint has better model capacity. The second property is sampling based or not. For example, gradient penalty requires sampling data from finite training set. On the contrary, spectral normalization only depends on model architecture. From this definition, non-sampling based methods are expected to perform better due to its generalization ability. The last one is hard or soft constraint, which is used to describe the boundary value of constraint. For example, gradient penalty is a kind of regularization, so the boundary value is not fixed during training. However, boundary value for spectral normalization is fixed, which can provide better constraint during training. In summary, previous methods do not satisfy these three properties at the same time, and the hard property is the most challenging one for GAN. So we want to propose a new normalization which can take the advantages of gradient penalty and spectral normalization. The gradient normalization is in the following formulation. The discriminator d of x is divided by the gradient norm plus absolute value of d of x. In Theorem 6, we prove that the gradient normalization has fixed boundary value, and this property holds for models which only contain piecewise linear activation functions. Until now, we know that the gradient normalization is a hard constraint. For the other two properties, we can observe the formulation and find that this method is only related to the gradient, which means gradient normalization is a model-wise and non-sampling based method. We also investigate the gradient with respect to discriminator parameters. As we can see, the first term in brackets is the objective of GAN, and the second term is the gradient regularization. These two terms control the weight of each other, and finally strike a balance during training. The gradient normalization can be used in different kinds of generation tasks. For unconditional image generation, we apply gradient normalization on DC GAN and ResNet-based architecture. The quantitative results outperform previous works in terms of inception score and FID on both CIFAR10 and STO10 dataset. In conditional image generation, the performance of gradient normalized big GAN outperforms the original one on CIFAR10. If we apply consistency regularization on gradient normalized big GAN, the result can further be improved. The gradient normalization can also be used in generating high-dimensional data. For example, the quality of generated human faces and church scenes are also of high quality. In conclusion, gradient normalization is a model-wise, non-sampling based, and hard constraint, so it can enjoy the benefits of stable gradient. Moreover, the concise formulation of gradient normalization makes it easy to incorporate into existing models or future works. Thank you for listening.